So, how do we know, really know, that a piece of code is correct, that it's going to do exactly what we want every single time with no errors? Yeah, that's a huge question, and it's what we're diving into right now.
When you really get down to it, almost every piece of software out there, from the OS on your phone to the code flying an airplane, it's all built on one core idea: repetition. Now, in the world of programming, there's a name for this. We call it iteration. And you can think of it as the engine of all software. It's what lets a tiny piece of code do a massive amount of work just by running over and over and over again. All right, so let's zoom in on this idea. Let's really look at this fundamental building block of code. We're talking about the part that does all that repeating, what every programmer just calls a loop. So these loops, the things that actually do the iteration, they usually come in two main flavors. First, you've got definite iteration. This is when you know exactly how many times you need to do something. Like do this 100 times. Simple. Then there's indefinite iteration. This is when you keep going until something happens, kind of like waiting for someone to click a button. You have no idea when they'll do it, but you know you've got to wait for that click.
And this is where things get tricky. If a loop runs a million times, how can you be sure it's right on every single one of those runs? You can't just test it a million times. So how do you prove it's correct? Not just the first time or the 500th time, but on that millionth run too. It's a huge problem.
Well, the answer to a question that big, it lies in a really fascinating field called formal program verification. So, program verification isn't just about testing. It's not about running your code with a few different inputs and hoping for the best. No, this is about creating a rock-solid mathematical proof that your software is correct for all possible inputs. And that, as you can imagine, is an incredibly high bar to clear, especially when you're dealing with loops. Okay, so how on earth do you do that? Well, one of the classic ways is something I like to call the step-by-step proof. Let's break it down. This whole idea is built on a really powerful concept called a loop invariant. Okay, think of it this way. Imagine a quality control inspector on an assembly line. An invariant is like a rule that inspector checks. It has to be true before the item even gets on the line. It has to be true after the first step. It has to be true after the second step, all the way to the very end. It's a condition that never ever changes. It's invariant. And the logic behind it is just so cool. It works in 3 steps. First, you have to prove that your special condition, your invariant, is true before the loop even begins. That's the foundation. Second, you have to prove that if it's true at the start of any single trip through the loop, it's still going to be true at the end of that trip. And finally, if you've done those 2 things, you can use that invariant property to prove that when the loop finally finishes, the result is exactly what you wanted. See? It's like building an unbreakable chain of logic, one link at a time. But wait, that's not the only way to tackle this problem. There's a totally different philosophy, one you can think of as the before and after promise. This method uses something called a loop contract. Now remember our quality control inspector? Well, this inspector doesn't check every single station on the assembly line. Nope, this one only checks 2 things. The raw materials going in, that's the precondition, and the finished product coming out, the post-condition. It basically says, look, I don't care what happens in the middle, as long as you start with good stuff, you better give me the right result at the end. So you see, the logic here is completely different. You're only checking 2 things. 1, are the starting conditions the precondition met before we even start? And 2, does the loop guarantee that the final result, the postcondition, will be true when we're done? It's all about trusting the process in the middle to do its job. Okay, so we've got these 2 really powerful ways of thinking, invariants and contracts. Let's put them side by side so we can really see how they're different. And here's the fundamental difference, right? The invariant philosophy is all about asking what's true at every single step. It follows the code as it runs. But the contract philosophy asks a different question: what goes in and what comes out? It's so different, in fact, that you can even work backward from the result you want to figure out what you needed at the start. Okay, let's get concrete. Imagine we're writing code to find the biggest number in a list. Using the invariant approach, we'd focus on what's happening at every single step. We might say something like, at every point in time, the true maximum value is guaranteed to be somewhere between these 2 moving markers. It's all about the process. Now, the contract approach,
It totally ignores the middle steps. It just makes a simple promise. If you give me a valid list to start, then I guarantee the final answer will be the biggest number from that list. See the difference? One describes the journey, the other just guarantees the destination. So the obvious question is, which one's better? Well, it turns out that might be the wrong way to look at it.
There's this great quote from researcher Gideon Ernst and his team that really nails it. They basically say that contracts are a really useful way to think about correctness, and it's conceptually different from invariance, but the technical stuff you need to support it is pretty minimal. The big takeaway is that these aren't competing ideas. They're just different ways of thinking, different languages to describe the same exact truth.
And that's the key right there. It doesn't matter which path you take. Whether it's the step-by-step invariant or the before and after contract, they both lead to the same exact place. Code that you can prove is correct.
So why does this even matter? Why have two ways to do the same thing? Well, because some problems are just easier, more natural to think about one way over the other. Having both options in the toolkit gives developers flexibility. It makes it easier for them to write these proofs in the first place. It lets us separate how we think about the problem from the tools that actually check our work. And the end result of all this? More reliable, more secure software for every single one of us, in our banking apps, in our cars, even in medical devices. And that leaves us with one last, really big question to think about. As these tools get better and more common, we're slowly shifting from a world where programmers say, I hope this works, to one where they can say, I can prove this works. So my question to you is, if we can truly guarantee our code is correct, what kind of impossible software can we finally build next?